All right, thanks for the reminder. So as I was saying, from the Schrodinger equation, we get the orbitals. The orbitals are the allowed states for the electron, and there are going to be three quantum numbers that define the orbitals: n, l, and m. Okay, so when we build up the allowed states, we can actually generate all infinite of them, and they're multiple patterns. So we're just going to look at the main patterns to figure out these orbitals. And so starting off, the lowest energy orbital possible is going to have n equals 1. N is called the principal quantum number, and that gives you pretty much the energy. So n equals 1 is the lowest energy, n equals 2 higher energy, and the allowed n values are integers up to infinity. So n equals infinity is the highest, and so there's going to be an infinite number of n's. But there's also an infinite number of forbidden n's. So for example, we can't have an n equals 1.1 or an n equals 1.25. It has to be 1 or 2 or 3, etc. And so the lowest energy will start with n equals n. N equals 1. When we have n equals 1, then we look at the next quantum number, the angular momentum quantum number, which is L. And so the L values are going to range from 0 up to a maximum of n minus 1. So it's going to take all values. And so when we have n equals 1, L can equal 0, but L cannot equal 1. If L equals 1, then that exceeds the maximum value allowed for L, which is n minus 1, which would be 1 minus 1, 0. 0 would be the maximum. So we're only allowed one L value. Why? Because if you had an L, let's say an n equals 1 and an L equals 1, then it would not satisfy the Schrodinger equation. In fact, the Schrodinger equation would forbid it. And so that would be a forbidden energy level or energy state for the electron or orbital for the electron. So when we build this, we're going to have n equals 1, L equals 0. Well, when L equals 0, we have a numerical and alphabetical system for that. So when L equals 0, we call it an s orbital. And so the s, that'll tell us pretty much the shape of the orbital. So L's representative of the shape. And so it would be a spherical electron cloud, kind of like the bird's nest we were talking about earlier. Okay, so when L is equal to 0, then what are possible m values? Our possible m values are going to be all integers through 0 that go from minus L to plus L. So if we go from minus 0 to plus 0, that only leaves one value of m, the magnetic quantum number. And so the magnetic quantum number is going to tell us the number of orbitals and the orientation. So m equals 0 tells us there's only one orbital with one orientation, the m equals 0 orientation. And so the first orbital is going to be a 1, 0, 0 orbital. So we call it NLM, NLM 1, 0, 0. All right, are you guys following along okay? I'm using my iPhone app right now, that's fine. And, it's cutting off. Okay. How about now? Is it okay now? Okay. Yeah. So as I was saying earlier, we're just figuring out the allowed states. So we just knocked off one, the 1, 0, 0. Now, how many more are there? Well, there's pretty much an infinite number But we don't have to generate all infinite. We're just going to start and maybe generate up to n equals 5 or so. That should be more than enough. So yeah, nobody can see anything because I'm not sharing the screen right now. I can't share the screen because I'm on my iPhone. But shortly, well, not shortly, but in about 30 minutes, I'll be on the computer. You should be able to see it then. So can you follow along? What we're going to do is we're going to draw one. So have a blank sheet of paper and label it the energy level diagram. So energy level diagram. And what we're going to do is we're going to generate the energy level diagram. At the bottom of the energy level diagram, we'll have our lowest energy state. And the energy level diagram is going to plot energy on an arbitrary y-axis. And so we'll just put, we'll put one horizontal line, small line, and call that the 100 orbital. Or alternatively, you could label it 1s. We'll label it both, 100 and 1s. The 100 stands for NLM. NLM is a unique address. You can think of it for the orbitals. Each orbital has a unique address. Okay, so that's the only orbital with n equals 1. So we have to go to the next level. The next level is n equals 2. When we go to the n equals 2 orbitals, those orbitals are typically, higher in energy, yes. And they have about, let's say, roughly, 4 times the energy, say. And they're going to be about 4 times the size. Actually, we'll look at it, size, energy in more detail later. But the next set of orbitals will have n equals 2. And when we get to n equals 2, we can figure out how many total orbitals there are, because there's another pattern that comes up, and that is the total number of orbitals is equal to n squared. So when we're at the n equals 1, that's 1 squared, which is 1. That gives us 1 orbital. But when we go up to n equals 2, we're going to have 2 squared, which is going to give us a total of 4 orbitals. That's a pattern. But these 4 orbitals aren't all identical. These 4 orbitals are divided into what we call sub-levels, or sub-shells, or sub-energies. And so it's different ways of thinking about it. So what are they? So when n equals 2, then we look at the next quantum number, which is L. And so we're going to have L equals 0, that's allowed, and we will have L equals 1. That would also be allowed. But L equals 2 is forbidden. The reason L equals 2 is forbidden is because L has a maximum of n minus 1, which in this case would be 2 minus 1, which is 1. And so the next one, L equals 3, 4, 5, etc., are all going to be forbidden. And so we only have the 2s when L is equal to 0, that's an s orbital, or we'll have the 2p. When L equals 1, we have a p shape. Now, an S shape is spherical. However, the P shape is not. The P shape looks like a figure 8 or a dumbbell. It's going to have two what we call clouds, centered about the nucleus. One on one side of the nucleus, the other on the opposite side of the nucleus. They're going to be oriented 180 degrees from each other, but that constitutes one orbital and one allowed energy. So, so we have the 2s and the 2p. Okay, when we go back to the 2s, that's n equals 2, L equals 0. Our possible m value is from minus L to plus L, so minus 0 to plus 0. And so there's only one, and that's 0. So we have the 2, 0, 0 orbital. But something happens when we get to L equals 1. When we get to L equals 1, you know, the 2p orbital, we go from minus L to plus L. And so L is equal to 1. And so if we go from minus L, which would be minus 1, to plus L, which would be plus 1, and we go through 0. So we hit the integers going through 0. And so we have actually 3 allowed values. We have minus 1, 0, and plus 1. So those would be the 3 allowed values. And so the first orbital is going to have this set of quantum numbers. It's going to have the 2, 1, minus 1. The next orbital is going to be the 2, 1, 0. And then that's going to be followed by the 2, 1, 1, and LM. And so those are what we call our 3 2p orbitals. Now those 3 2p orbitals all look the same. The only difference is their orientation. One is oriented, if we do an XYZ coordinate system, one is oriented on the x-axis, the other is oriented on the y-axis, and the last one's oriented on the z-axis. So they're identical, the only difference is the orientation. And so what the magnetic quantum number tells us, M, the magnetic quantum number tells us the number of orbitals, the total number of orbitals. And so there are 3 total orbitals, a minus 1, a 0, and a 1. And then it tells us our orientation. So from the Schrodinger equation, we could figure out which one's the x, which one's the y, which one's the z, but we don't need to worry about that. We just need to know that there are 3 2p orbitals. We can label each of those as a 2p orbital, but that's not unique. So what we need is a unique address for each of those. So we're going to draw 3 lines. If you look at the energy level diagram on the PowerPoint, you'll see that the 2p orbitals are slightly higher in energy than the 2s orbitals. And they're written offset to the right so that we can separate the types, we call them subshells, the S subshell from the P subshell. So we're going to have 2 subshells in n equals 2. And that would be the 2s orbital, it's just 1, and the 2p orbitals, the 3 of those. So that's it. All right, then we'll go on to, well, we can't go on there because we've maxed out the L, and there are no more L's. And so we have to bump up to the next energy. The next energy is going to be the 3, n equals 3. Now, if you're visualizing an n equals 2 orbital, which is, versus n equals 1 versus an n equals 3, you know, the difference is two things. One is the energy. You know, the higher the n, the higher the energy. And the higher the energy, the bigger the orbital. And so let's compare like a 1s orbital to a 2s orbital. 1s orbital is about, just draw a small sphere, but in relative terms, the 2s orbital is going to be about 4 times bigger. Now, when we go up to a 3s orbital is going to be about 9 times bigger. And it's going to have significantly more energy, or be a higher energy orbital. And so let's go to n equals 3. Now, when n equals 3, how many subshells do we have? Well, let's take a look. The subshells are given by L. And so when we look at L, when n equals 3, L, we have 3 possible values. In fact, the number of subshells is equal to n. So for example, when n equals 1, we had 1 subshell, the 1s. When n equals 2, we had 2 subshells, the 2s and the 2p subshells. And the 2p had 3 orbitals, the 2, 1, negative 1, the 2, 1, 0, and the 2, 1, 1. When n equals 3, we're going to have 3 subshells in that. And so what are the 3 subshells? Well, the 3 subshells are going to be when L equals 0, that's allowed. That would be a 3s. We're also going to have when L equals 1, that's also allowed. That would be a 3p. But now we're going to have L equals 2, which is allowed. L equals 2 is what we call a d orbital. And these would be n equals 3, L equals 2, that would be a 3d orbital. So, so we have those, and then if I try to go up one more, like an L equals 3, then that violates the Schrodinger equation, basically. So I can't go up to L equals 3. So just L equals 0, S, L equals 1, P, and L equals 2, D. So 3S, 3P, and 3D. Now, how many? What is the number of orbitals in each subshell? And what is their orientation? Well, that's going to be given by M, the magnetic quantum number. And so we saw with the 3, 0, that's a 3s, we only have one value of M allowed. That's 0, so it's a 3, 0, 0 orbital. Now, when we have L equals 1, we can go from minus L to plus L. So minus 1 to 0 to 1. So if we go minus 1, that's the 3, 1, minus 1. That would be the first of the 3p orbitals. Then we go to L equals, M equals 0. That would be the 3, 1, 0. And then M equals 1. So M goes from minus 1, 0, plus 1. So 3 values. 3 values means 3 orbitals and 3 orientations. So we're going to have 3 3p orbitals. Now, those are all equal in energy. You know, again, the shape is exactly the same. It's just the orientation is different. Okay, now when we go to L equals 2, L equals 2 will have allowed M values of minus L to plus L. So minus 2 to plus 2, and it's going to go through all integers and 0. So we go, let's say, minus 2 to minus 1 to 0 to 1 to 2. And so if you count those, that's going to be 5. You know, minus 2, minus 1, 0, 1, 2. That's 5 different values. So that means there's 5 orbitals. Now the orbitals are kind of the same shape. 4 of them are exactly the same shape. The 5th one is different in shape, but all 5 have the exact same energy. And so we have 5 orbitals with 5 orientations. And so those are the D orbitals, the 5D orbitals. Now it's going to give us a total of 3 squared orbitals in the n equals 3 shell, or n equals, we'll say n equals 3 energy level. There's 9 orbitals, 3 squared. And so we have the 3s, which is 1 orbital. We have the 3p, which is 3 orbitals. And then we have the 3d, which is 5 orbitals. So that gives us 9 orbitals. So these patterns will help us sometimes when we go to higher energy levels and we try to figure out what the possible orbitals are. So we'll continue on here. N equals 4. And actually, you want to build up the table up through maybe the 4p orbitals. But when n equals 4, we expect to see 16 orbitals with an n equals 4. It's 4 squared, so a total of 16 orbitals. Now, what are the orbitals? Well, how many subshells do we have? Well, we're going to have 4 subshells. And so we should have an S subshell, a P subshell, a D subshell, and what comes after the D? After the D is going to be the F subshell. once we get to F, then it goes alphabetical. So it goes S, P, D, F, and then the next one would be G, H, I, J, K, etc. And so, since we have an infinite number of those, we have to continue with this system, make it work. Pretty soon, the lettering becomes cumbersome, and it's just better just to use numbers rather than letters to designate the orbitals. But anyway, when n equals 4, we expect to see 4 subshells. So we're going to have the L equals 0, which is the S, the L equals 1, which is the P, the L equals 2, which is the D, and the L equals 3, which is the F. Okay, so building those orbitals up using quantum numbers. So we have those, all those L values are allowed. L equals 4 is forbidden, and anything beyond that's forbidden. And so when n equals 4 and L equals 0, we have 4s orbital. And when we have a 4, 0, the only m value is 0, so it's a 4, 0, 0 orbital. You know, one orbital, one orientation, which is a spherical shape. And so if we look at the size, you know, the size compared to 1s orbital, a 4s orbital is about 16 times bigger. The size is roughly given by n squared, you know. So for example, let's start off with a 1s orbital, and then we'll go to 2s orbital. 2s orbital is roughly 4 times bigger. You know, orbitals, the size is tricky. And so in Chem 1A, you'll learn more about the sizes of orbitals, but we'll just take that as a rough. Then we'll go to n equals 3, which is 3 squared, about 9 times bigger. And then n equals 4, which is 4 squared. So a 4s orbital is about 16 times bigger than a 1s orbital. And so the size of the orbital is important because you know, it tells us about the distance from the electron could be from the nucleus. Continuing on, so we got n equals 4, L equals 0, m equals 0. That's our first allowed orbital, and n equals 4. That's a 4s orbital. Now, slightly higher in energy would be the 4p orbital. Now, the 4p orbital is going to have n equals 4, L equals 1. When L equals 1, we have 3 m values that are allowed. 1, 0, and minus 1. So we're going to have the 4, 1, 1, the 4, 1, 0, and the 4, 1, minus 1 orbital. And that gives us our 3 4p orbitals. The 4p orbitals are going to be much bigger than 3p orbitals, which are much bigger than, you know, 2p. There's no such thing as a 1p orbital because that would violate the Schrodinger equation. And so 2p is where it starts. And so there's also some other things about the shape of the orbital, which we'll talk about, things called nodes, which have a 0 probability of finding electrons. Okay, once we go to the 4p, then the next will be the 4d orbitals. The 4d orbitals are going to have n equals 4, L equals 2. When L equals 2, again, we had the minus 2, minus 1, 0, 1, 2 allowed m values. There's a total of 5 allowed m values, so there's a total of 5 orbitals that are allowed, and they have different orientations. We don't have to worry about the orientations. And so the 4d orbitals can be labeled 4, 2, minus 2. That would be the first one. The second one would be 4, 2, minus 1, 4, 2, 0, 4, 2, 1, and 4, 2, 2. So each individual orbital would have a unique set of 3 quantum numbers identifying it, so we know exactly which orbital we're talking about. Okay, and then finally, we have L equals 3 allowed. When L equals 3, then our possible m values are minus 3, minus 2, minus 1, 0, +1, +2, and +3. So if we think about it, you know, it's the number of orbitals that are allowed for a subshell is given by 2L plus 1. 2L because we have the negative side and the positive side, and the +1's the 0 going through the 0. So for example, when L equals 3, we should have 2 times 3 is 6 plus 1, 7 orbitals. And so when L equals 3, the F orbitals, we should have 7 orbitals. When L equals, we can't have L equals 4, but if we had L equals 4, then we'd expect 2 times 4 is 8 plus 1 is 9 orbitals. So the G subshell should have 9 orbitals. When L equals 5, it's 2 times 5 plus 1, 11 orbitals. The H subshell should have 11 orbitals, etc. And so we can figure it out, you know, if we had 100, let's say L equals 100, we'd have 201 orbitals in the L equals 100 subshell. And so it's easy to figure out once we have a mathematical pattern to it, and then we could figure out all the way out to infinity. If we wanted, it'd just take an infinitely long time to generate every single orbital, but we could do it because the mathematical pattern is not too difficult. Okay, so so that's what we have built up. We'll just do let's say one more to figure it out. If we do n equals 5, how many orbitals are there? Well, n equals 5, how many subshells do we expect? So n equals 5, how many subshells with an n equals 5? Yeah, 5 subshells. In those 5 subshells, how many total orbitals are you going to have? And so what would the total number of orbitals be in those 5 subshells? Okay, 11 would be the number of orbitals in a subshell, but what I'm asking is the total number of orbitals with an n equals 5. We'll talk about 11 in a minute, but the total number, I'm not saying L is equal to 5, I'm just saying n is equal to 5. When we have n equals 5, we'd expect to find how many orbitals with an n equals 5. Okay, the numbers that I'm looking for is 25. You know, so n equals 1, how many orbitals are there? This is just the pattern. N equals 1, there's 1 orbital, the 1s orbital. When n equals 2, how many total orbitals are there? There are 2 squared, which is 4. There are 4 total orbitals. The 2s has 1, and then we have 3 2p orbitals, so it gives us a total of 4 orbitals. When n equals 3, we should see 9 total orbitals in 3 subshells. The 3s has 1 orbital, the 3p has 3 orbitals, and the 3d has 5 orbitals. So this altogether 9 orbitals. And so we can build up that pattern. And so when we go to n equals 4, we saw 16 orbitals divided into 4 subshells, not evenly, because the 4s only had 1, the 4p had 3, the 4d had 5, and the 4f had 7. Now, when we go up to n equals 5, we expect to find 25 orbitals divided into 5 subshells. What are the 5 subshells? The 5 subshells are going to be the L equals 0, which is the L equals 1, which is the P, the L equals 2, which is the D, and the L equals 3, which is the F. Now we have one more subshell, and that would be after F, A, B, C, D, E, F, G. That would be the G subshell. And so that's when we're going to have L equals 4. Now, the G subshell is new. How many orbitals are there in the G subshell, in the L equals 4 subshell? Well, we can either count them and use the little equation. If we count them out, it would be -4, -3, -2, -1, 0, +1, +2, +3, +4. And so if we counted them out, it would be 9 orbitals altogether. Or we could use the mathematical pattern. The mathematical pattern would be 2L + 1. So it's 2 times 4, which is 8. And that covers, you know, the -4 countdown to the +4 countdown. And then the +1 is the 0, going through the 0. So it takes care of the all 25 orbitals there. All right, so that's how we generate the orbitals, and we can generate. I mean, if we wanted to, we could go to n equals 100. You know, n equals 100. How many orbitals are there? Well, there's going to be 100 squared. So 100 squared would be 10,000, right? And so 10,000 orbitals divided into 100 subshells, and then we'd have to figure out all the subshells. The subshells are easy if we just leave it numbers rather than lettering them. If we just left it numbers, the subshells would just be subshell L equals 0, subshell L equals 2, all the way up to subshell L equals 99. Now, L equals 99, I don't know what letter designation they call that, you know. I mean, we'd have to sit there and figure it out, or, I mean, we could figure it out because it'd just be some pattern, but you get to a point where the letter designation is useful, you know, and get very high numbers. And so that's good. So what I'm going to do is, let's see, it's 12:06 right now. I'm going to set up so we can see visual. And so let's take a break. We're going to take an early break and a little bit extended break. So let's take like a 20-minute break, sorry, and then we'll come back and then I'll have the computer up. All right? And so early break time, because I want to get my computer set up here. So early break time. And so we'll meet back in about 20 minutes, okay? And then by then I'll have the visuals up, so you just won't have won't be listening to audio. I have to close this right now, but the room, I mean, I'll be leaving the room shortly, but I'll be back.